Welcome to this workshop on meta-analysis. This video is one in a series, and I recommend this one if you plan to work with the standardized mean difference or the mean difference. This video includes both a basic section and also an advanced section. I'll cover the following items: how to enter data, how to run the analysis, how to estimate the mean effect size, how to understand heterogeneity in effects, how to report the results, and how to create plots. I will also cover the following topics: how to perform a subgroups analysis, how to perform a meta-regression, and how to assess the potential impact of publication bias. I'll be using the software Comprehensive Meta-Analysis, or CMA. Our website is metaanalysis.com. There, you can download a free trial of the software and also the datasets used in this video. This analysis is discussed in our text, Introduction to Meta-Analysis, 2nd edition, and in our book, Common Mistakes in Meta-Analysis and How to Avoid Them. The concepts are also discussed in the book, Systematic Reviews in Healthcare, 3rd edition. This analysis includes 17 studies that look at the impact of methylphenidate on cognitive function in adults with attention deficit hyperactivity disorder, or ADHD. All studies were randomized controlled trials, RCTs, in which patients were randomized to either methylphenidate or to a placebo. At the conclusion of each study, patients were assessed on some scale of cognitive functioning. Each study reported the mean score for the treated and control groups. The effect size index is the standardized mean difference, D. This example is based on data from a systematic review that was published by Castells et al. In 2011. If you're interested in the specifics of this analysis, please don't rely on this video, but consult the original paper. First, let's look at the data in Excel. The file is called adhd.xls. This is based on the data in the original paper. I've changed the format of the data for purposes of this tutorial, but this has no impact on the results. There's a column here with the study names. There are 3 columns for the treated group. We have the mean, the standard deviation, and the sample size. And there are 3 columns for the placebo group. We have the mean, the standard deviation, and the sample size. There are also some columns with potential moderating variables, and we'll discuss those later. I wanted to copy this data into CMA. I'll highlight all the relevant cells. Notice that I'm including the row with the labels. I click Ctrl-C to copy. I'll open CMA. I'll close this box. I click in this cell, and I press Ctrl-V to paste. I want to take these labels and move them into the header. I click Format, use first row as labels. At this point, the labels are correct, but I still need to identify the function of each column. On the menu, there's a button that I can use to insert columns, and there's a separate button that I can use to identify the function of columns that already exist. Since the columns are already in the grid, and I want to identify their functions, I'll use identify rather than insert. I click on the first column. And then I click Identify Column for study names. The program changes the header to Study Name. I click Identify Column for effect size data. The program opens this wizard. CMA will accept data in many formats, so I need to tell the program which format I want to use. I also have the option of entering data for some studies in one format, for other studies in a second format, and so on. At the bottom, I choose Show All 100 Formats, and I click Next. This is the option that will allow me to compare two groups. I choose that, and I click Next. On this frame, I choose Continuous Data Means, because I'll be comparing the means in two groups. In our studies, patients were randomized to either treatment or control and were assessed only at the end. So I choose Unmatched Groups, Post Data Only. Then I choose Mean, Standard Deviation, and Sample Size in each group, since that's the format we'll be using. If I were inserting these columns, the Finish button would light up. Since the columns already exist, and I need to match each column with its function, the Next button lights up. And I click Next. Here, I need to identify the column that holds the mean for the treated group. I click here and I select TX mean. That's the label that had been used in Excel and then moved into CMA. I need to identify the column that holds the standard deviation for the treated group. I click here and I select TX SD. I need to identify the column that holds the sample size for the treated group. I click here and select TXN. I need to identify the column that holds the mean for the placebo group. I click here and select PBO mean. I need to identify the column that holds the standard deviation for the placebo group. I click here and select PBO SD. And I need to identify the column that holds the sample size for the placebo group. I click here and select PBON. Finally, I need to identify the column that holds the effect direction. I'll discuss that a little later, but I don't have it, and so I will skip it, and I click Finish. The program has now created a set of columns to hold the data. These columns are labeled Group A, and these are labeled Group B. This panel allows me to assign more descriptive names. I'll use drug and placebo. Now these columns are drug, mean, standard deviation, and sample size. And these are placebo, mean, standard deviation, and sample size. Finally, we have a column called effect direction. If I click on any cell in this column, the program opens a drop-down box with three options. These are auto, positive, and negative. Auto means that the program will compute the difference as mean 1 minus mean 2. And that's what I want. I click auto for this cell. As soon as I do that, the program computes the effect size and displays that here. Then I can use Control-C to copy this cell. I highlight all the other cells in the column, and I click Control-V to paste. And now the program displays the computed effect sizes for all the studies. In this analysis, I'm able to use auto for effect direction because the direction has the same meaning in all the studies. In other words, all studies employed a scale where a high score was good. So a positive difference always means that the treated group did better, and a negative difference always means that the placebo group did better. On the other hand, if there had been some studies where a high score was good and other studies where a low score was good, we would not be using auto. Rather, we would assign a designation of positive whenever the treated group actually did better, and we would assign a designation of negative whenever the placebo group actually did better. By default, the program is displaying 3 effect size indices. This is the standardized difference in means, sometimes called Cohen's d. This is an alternate version of the standardized difference in means, sometimes called Hedges G. And this is the raw difference in means. I'm going to use the standardized difference in means, Cohen's d. Since I'm not using the other columns, I'd like to hide them. To modify the display, I can right-click on the yellow columns, and I click the option to customize the display. The program opens this wizard. By default, the program has checked the 3 effect sizes that we just discussed. I'm going to remove the check mark for Hedges G, and I'm going to remove the check mark for the difference in means. At the bottom, I can check the option to show the standard error, and I can check the option to show the variance. And then I click OK. Now the program is displaying the standardized difference, Cohen's d, along with the standard error and the variance of that effect size. I will also need to assign a function to these other columns. I'll come back and do that later. This would be a good time to save the file. I click the Save icon and I give the file a name. Before I leave this screen, let me point out 2 things. If I wanted to see the formula that was used to compute the effect size, I can double-click on any cell and see the formula. Also, in this analysis, all studies reported data in the same format. But I also have the option to mix and match formats. For example, if some studies had reported simply a p-value and sample size, I could work with that. And if some studies had used a match design or pre-post designs, I could work with that. The program would take the data as entered for each study and use the appropriate formula to compute the effect size and variance for that study. And then all of the studies, regardless of their original format, could be included in the analysis. I click Run Analysis. Here, I can select an effect size index. I'll be using the standardized difference in means. At the bottom of this screen, I can choose either the fixed effect model or the random effects model. I choose the random effects model for 3 reasons. First, it allows me to take account of the study-to-study variance when assigning weights to each study. Second, it allows me to assess the dispersion and effect size across studies. And third, this model will allow me to generalize from the studies in the analysis to the universe of comparable studies, which is what I intend to do. Next, I'd like to set the scale for the forest plot. I right-click on the plot, I select Scale, and I set the scale to -2 to +2. I'd like to sort the studies by effect size so that I can get a general sense of how widely the effect size varies across studies. I right-click on the column labeled Standardized Difference in Means, and I click Sort from Low to High. I get the sense that the effect size in most studies falls in the range of around 0 to 1. But there are a few studies with effect sizes outside that range. In any event, this is only intended to give me a general sense of the dispersion. We'll compute the actual dispersion momentarily. These columns show the statistics in numbers, and these are also plotted here. Since we're dealing with a standardized difference in means, the null value is 0. In this analysis, anything to the left of 0 indicates that the placebo group did better, and anything to the right of 0 indicates that the treated group did better. Each row displays data for one study, and there are 2 rows for the summary effect here and here. To understand what these rows tell us, let me take a step back and explain the goal of a random effects analysis. When we perform a random effects analysis, we assume that there is a universe of potential studies that we care about. In this case, it might be all studies that could be performed to assess the impact of methylphenidate on adults with ADHD. I'll refer to that as the universe of comparable studies, or simply the universe. We assume that our 17 studies are a random sample from that universe, and so we can use these studies to make an inference to that universe. The analysis has 2 goals. The first goal is to report the mean effect size in this universe. The second goal is to report how widely the true effect size varies across studies. With that in mind, let's have a look at the analysis. This line gives me the mean effect size. The mean effect size is estimated as 0.506. The confidence interval is 0.362 to 0.651. That tells me that in the universe of comparable populations, the true mean probably falls in this interval. If we wanted to test the null hypothesis that in the universe of comparable populations, the mean effect size is 0, the z-value for that test is 6.857, with a corresponding p-value of less than 0.001. We see that here, and we also see it here in that the confidence interval excludes 0. We would reject the null hypothesis that the mean effect is 0 and conclude that, on average, the treatment is helpful. Next, we want to ask about the dispersion in effects. To be clear, we do not want to simply report the lowest and highest effects that we see here. If we did that, we would be basing our results on 2 studies and ignoring the information from the other 15. Rather, we want to use the dispersion in effects across all 17 studies to estimate how the effects are distributed in the universe that we care about. To compute the actual amount of dispersion, we do something similar to what we would do in a primary study. We compute the standard deviation of true effects, then we compute an interval based on the mean plus or minus 2 standard deviations. If we can assume that the effects are normally distributed in the relevant units, we would expect that the true effect size in 95% of all comparable populations will fall within that interval. Before I explain how we do that, I want to address 2 common mistakes. Some researchers think that the confidence interval tells us something about the dispersion in effects. For example, they might think that the effect size in individual studies ranges from here to here. That is absolutely wrong. The confidence interval is an index of precision, not an index of dispersion. It tells us how precisely we have estimated the mean. It says nothing about how widely the effect size varies. A second common mistake is that people think that the I-square statistic tells us how much the effect size varies. While this is a very common mistake, it is still a mistake. The I-square statistic does not tell us how much the effect size varies. I discussed this in other videos and papers. For now, I'll simply make the following point. In this analysis, I-squared is 47%. On that basis, how much does the effect size vary? The answer is there is no way to know. The I-square statistic simply does not provide that information. In a variant of this mistake, researchers sometimes use I-square to classify the heterogeneity as being low, moderate, or high. These classifications are meaningless for two reasons. First, they're based on I-square, and I-square does not tell us how much the effect size varies. It follows that any classification based on I-square also cannot tell us how much the effect size varies. Second, the classifications are not informative. For example, what does high heterogeneity mean? Does it mean that there are populations where the effect size is as high as 0.8? Or does it mean that there are populations where the effect size is as high as 1.2? Or does it mean that there are populations where the effect size is as high as 1.6? There is no answer. The idea of classifying heterogeneity using these terms is simply not useful. So, what statistic does tell us how much the effect size varies? Well, that statistic is the prediction interval, which is displayed on this row. The prediction interval is 0.058 to 0.954. And this is also plotted here. At one extreme, there are some populations where the drug will increase cognitive function by roughly 0.05 standard deviations, which in this context is a trivial impact. At the other extreme, there are some populations where the drug will increase cognitive function by roughly 0.95 standard deviations, which in this context is an exceptional impact. Why is this called a prediction interval? Well, suppose someone was thinking of using this medication for a new population. They ask me how well the treatment will work in this population. I would predict that the effect would fall somewhere between here and here. And I'd be correct for some 95% of all populations. To recap, these two lines address two distinct issues. This line deals with the average effect. The average effect falls someplace between here and here. And this line deals with dispersion in effects. In any single population, the true effect size could be as low as this or as high as this. I can also create a high-resolution version of this plot. I'll discuss later how to create that plot, but right now I want to show one thing. These two rows are the same as the ones we saw a moment ago. This row displays the mean effect size and its confidence interval. Here, the confidence interval is displayed using a horizontal line as it was in the prior plot. We can also display it using a diamond, which is a common convention. But whether we use a line or a diamond, the meaning is the same. This line represents the confidence interval. It tells us how precisely we have estimated the mean effect. It says nothing about the dispersion in effects. For dispersion, we turn to this row, which displays the prediction interval. In any single population, the true effect size will usually fall between here and here. CMA can also create a second plot, which takes the information in these two rows and presents it in a more intuitive format. If I click this button, the program generates this plot and these captions. This caption corresponds to this line. It reads, the mean effect size is 0.51 with a 95% confidence interval of 0.36 to 0.65. And this caption corresponds to this line. It reads, the true effect size in 95% of all comparable populations falls in the interval 0.06 to 0.95. The prediction interval, 0.06 to 0.95, reflects the endpoints of this distribution. And this is a useful way of summarizing the plot. But When it is possible to display the entire plot, we should do so, since it provides a more nuanced look at the distribution. The prediction interval told us that there were some populations where the effect was as low as 0.06 and others where it was as high as 0.95. The plot gives us a more detailed view. For example, I can see that in most populations the effect falls somewhere between here and here. In only a relatively small number of populations does the effect fall in this range or in this one. Then I can edit the labels, and I can send this to Word or to PowerPoint. To see additional statistics, click Next Table. This screen is divided into two parts. The left side of the screen deals with the mean effect size, and the right side of the screen deals with heterogeneity. I'm going to use the statistics for the random effects model, and these are the same statistics that we saw on the prior screen. Here are the mean and its confidence interval. Here are the z-value and the p-value. Then let's look at the heterogeneity. For heterogeneity, some of the statistics are presented on this row and some are presented on this row, but they all apply to the random effects model. Here we have the q-value along with its degrees of freedom and p-value. Here we have tau and tau squared. Here we have the I-squared statistic. And here we have the prediction interval. If you'd like to learn about these statistics, I have a paper that you can download for free on our website. That paper is an excerpt from our book, Common Mistakes in Meta-Analysis and How to Avoid Them. For now, I'll only make the following point. Each of these statistics addresses a specific question. We need to be clear about what question we intend to ask, and then we need to apply the appropriate statistic. One question we can ask is, does the true effect size vary at all across studies? For that, we turn to the q-value along with its degrees of freedom and p-value. If the p-value is less than the criterion alpha, we conclude that the true effect size does vary across studies. The criterion alpha for testing heterogeneity is sometimes set at 0.10 rather than 0.05. So any p-value under 0.10 would be considered statistically significant. In any event, the p-value here is 0.017, so we conclude that the effect size does vary. In other words, the drug has more of an effect in some studies than in others. The second question we can ask is the following. What is the standard deviation of true effects, or what is the variance of true effects? These values are given by tau and tau squared. A third question we can ask is the following. The dispersion that we see in the forest plot is partly due to variance in true effects and partly due to sampling error. So we can ask, what proportion is due to variance in true effects? That question is addressed by the I-squared statistic. In this case, I-squared is 47%. This tells us that 47% of the variance that we see reflects variance in true effects. The other 53% is simply sampling error. Note that 47% is a proportion. It does not tell us how much variance there is. The fourth question we can ask is the following. What is the range of true effects? Or, if I were to pick one population at random from the universe of comparable populations, what would the true effect size be in that population? That question is addressed by the prediction interval. In 95% of all populations, the true effect size falls between 0.058 and 0.954. In practice, papers typically report the Q value along with its p-value, and they report tau square and I square. A common mistake in papers that report a meta-analysis is that these statistics, especially I square, are interpreted as telling us how much the effect size varies. However, that is incorrect. They do not tell us how much the effect size varies. That question is addressed only by the prediction interval. There is one very important caveat to all of this. In order to estimate heterogeneity reliably, we need a minimum number of studies in the analysis. The number of studies needed will vary based on several factors. However, we might use 10 as a useful minimum to provide a sense of scale. When there is variation in the effect size, and there are less than 10 studies in the analysis, we cannot have confidence that any of the statistics related to heterogeneity will be reliable. And that includes I square and tau square, as well as the prediction interval. Now, let's have a look at how we might explain the results. In CMA version 4, I click this button, and the program displays this page, which reads as follows. Overview. The analysis is based on 17 studies. The effect size index is the standardized difference in means, D. Statistical model. The random effects model was employed for the analysis. The studies in the analysis are assumed to be a random sample from the universe of potential studies, and this analysis will be used to make an inference to that universe. What is the mean effect size? The mean effect size is 0.506 with a 95% confidence interval of 0.362 to 0.651. The mean effect size in the universe of comparable studies could fall anywhere in this interval. The z-value tests the null hypothesis that the mean effect size is 0. The z-value is 6.857 with a p-value of less than 0.001. Using a criterion alpha of 0.05, we reject the null hypothesis and conclude that in the universe of populations comparable to those in the analysis, the mean effect size is not precisely 0. The Q-test for heterogeneity. The Q-statistic provides a test of the null hypothesis that all studies in the analysis share a common effect size. If all studies shared the same true effect size, the expected value of Q would be equal to the degrees of freedom, which is the number of studies, minus 1. The Q value is 30.106 with 16 degrees of freedom and a p-value of 0.017. Using a criterion alpha of 0.1, we can reject the null hypothesis that the true effect size is the same in all these studies. The I-squared statistic. The I-squared statistic is 47%, which tells us that some 47% of the variance in observed effects reflects variance in true effects rather than sampling error. Tau squared and tau. Tau squared, the variance of true effect sizes, is 0.039 in D units. Tau, the standard deviation of true effect sizes, is 0.197 in D units. The prediction interval. If we assume that the true effects are normally distributed in D units, we can estimate that the prediction interval is 0.058 to 0.954. The true effect size in 95% of all comparable populations falls in this interval. Please note that my intention here is not to have the program write the report. I am simply trying to ensure that the statistics are interpreted properly. Along those lines, there's also an option to annotate this report and provide additional information. For example, if I click that option, the section on I-squared would read the I-squared statistic. The I-squared statistic is 47%, which tells us that some 47% of the variance in observed effects reflects variance in true effects rather than sampling error. Notes on I-squared. There's a common belief that I-squared tells us how much the effect size varies across studies. In some cases, I-squared values have been employed to classify the amount of variation as being low, moderate, or high. While this interpretation of I-squared is ubiquitous in some fields, it is nevertheless incorrect. I-squared is a proportion, not an absolute amount. It tells us what proportion of the variance in observed effects reflects variance in true effects rather than sampling error. It does not tell us how much the effects actually vary. The statistic that does tell us how much the effect size varies is the prediction interval, which is discussed below. Finally, the program inserts citations and references. The report can be exported to other programs such as Word. The core text is displayed in black, and the annotations are displayed in blue. Next, I want to create a high-resolution version of the forest plot. First, I want to modify this screen. Specifically, I want to hide some of the columns, which will leave more room for the remaining columns. I right-click in this area to open a panel. I'm going to remove the check mark for the standard error and the variance. And then I click OK. Now the screen looks like this. The columns that I had deselected are hidden. I click High Resolution Plot. I click Reset All. I right-click on the title. I edit the title to Methylphenidate for Adults with ADHD. I want to modify the symbol for the prediction interval. I right-click anywhere on the plot. I click Study and Summary Symbols. I select the tab for prediction intervals. I click here to increase the line width. And I click here to add a cap at either end. If I wanted to, I could set the color for this symbol. Next, I want to add additional space between the columns. I right-click anywhere on the plot. I select the tool for spacing and forest plot width. I select the tab for column spacing. Then I click the button with one blue arrow a few times. I'd like to increase the width of the forest plot graphic. I select the tab for forest plot width, and I click the button with two blue arrows. The two sides of the plot are labeled favors A and favors B. I know that the left should be favors placebo, and the right should be favors drug. I know that because I checked that on the data entry screen. Now I can enter those labels here. I right-click on favors A. I enter the labels favors placebo and favors drug. And I can change the font size. The footer reads Meta-Analysis. I right-click on the footer, and I edit it to read Random Effects. I'd like to send this to PowerPoint. I click File, Export to PowerPoint. The program opens PowerPoint and inserts the plot. In PowerPoint, I can display this full screen. I'll return to CMA. Back in CMA, I can choose colors for slides. I can modify any or all of the colors on the slide. And now, I'll send this back to PowerPoint again. If I wanted to, I could send this directly to Word, or I could save it as a file and then import it into any program. That's it for the basic analysis. When we analyze a primary study, we typically perform a sensitivity analysis. This means that we might perform a series of analyses to ensure that the results are robust. For example, we might want to ensure that the results were not overly influenced by one outlier. We can do something similar in a meta-analysis. Here, I'll outline some procedures that we might want to include as part of a sensitivity analysis. One issue we might want to explore is how much of an impact each study has on the analysis. Recall that the summary effect size is a weighted mean of the individual effect sizes. We might want to see how much weight was assigned to each study. If I click this button, I can display a column with the relative weight assigned to each study. Initially, these bars are on a scale of 0 to 100. To see the weights more clearly, I can right-click here, and then I choose Scale Relative to Maximum. This changes the scale so that differences among weights are easier to see. Additionally, I can sort by relative weight. I right-click on the weights. I select Sort from high to low. We can see that no study gets more than 11% of the weight. This tells me that I don't need to be concerned that any one study dominated the analysis. I also see that almost every study gets at least 4% of the weight. And this tells me that most of the studies played a role in the estimates of the mean effect and heterogeneity. Another type of sensitivity analysis is to ensure that the results are robust in the sense that the basic conclusions are not dependent on any one study. To look at this, we could run the analysis with only the first study removed, then with only the second study removed, and so on. CMA allows us to perform this sensitivity analysis with one click. First, I'm going to resort the studies by effect size. Let's focus on Spencer B, since this is the study with the highest effect size, which is 1.3. At the bottom of the screen, I have a tab for Basic Stats and a tab for One Study Removed. I click on the tab for One Study Removed. Now, the row labeled Spencer B does not show the results for Spencer B. Rather, the row for Spencer B shows the results for an analysis based on all studies except for Spencer B. On the row labeled Spencer B, the effect size is 0.467. And this is what we would see on the yellow line if we ran an analysis using the other 16 studies. Recall that the mean effect size with all 17 studies was 0.51. Now we know that without this study, the mean effect size would have been 0.47. So this study pulled the mean effect to the right from 0.47 to 0.51. From a clinical perspective, a mean effect size of 0.47 is essentially the same as a mean effect size of 0.51. So the essential conclusions would remain the same if we removed the study from the analysis. As I scan the set of analyses, I see that regardless of which study I remove, the basic conclusions remain unchanged. This row continues to show the original results, and if I compare each row to this row, I see that the mean effect size never moves to the left nor to the right by enough to change the clinical implications of the finding. If we're concerned about a test of the null hypothesis, the p-value is always less than 0.001. So this plot allows me to report that the results are robust in the sense that the conclusions remain essentially the same with any one study removed. I'll click Basic Stats and return to the Standard Analysis screen. Next, I'd like to perform an analysis for publication bias. The logic of publication bias is discussed at length in another module. Here, I'll focus on the results. I click Analyses, Publication Bias. The program displays what is traditionally known as a funnel plot. The large studies are plotted at the top, and the small studies are plotted at the bottom. This line corresponds to the mean effect size, and the diamond corresponds to the mean effect size and its confidence interval. Initially, the mean and confidence interval are based on the fixed effect model. Since we're working with the random effects model, I'll select that here. The mean and confidence interval now match those we saw on the main analysis screen. On the main screen, the anchor was at 0, and here the anchor is at the mean effect size. This makes it easier to see how studies vary about the mean. Most models of publication bias assume that most of the large studies have been published. That's because large studies tend to be statistically significant even when the effect size is relatively small. And even when these studies are not statistically significant, there are various incentives to publish them. Therefore, we expect all of the large studies to be published, and based on the laws of statistics, to be evenly distributed on either side of the mean. By contrast, we expect that only some of the smaller studies have been published. Specifically, small studies that reported large effects would tend to be statistically significant and likely to be published. By contrast, small studies that reported smaller effects might not be statistically significant and might not have been published. If there's no publication bias, we would expect to see large studies evenly distributed on both sides of the mean. And we would also expect small studies to be evenly distributed on both sides of the mean. On the other hand, if there is publication bias among the small studies, that would mean that there are studies missing over here. And so we would expect the mean for the small studies to be higher than the mean for the large studies. On that basis, most procedures that look for publication bias look to see if the mean for these studies is higher than the mean for these. In order for these procedures to be useful, we need to have a reasonable number of large studies and a reasonable number of small studies in the analysis. I don't think that we have that here. Small studies would appear down here, and we don't have many. Nevertheless, I'll run through these procedures to show how they are intended to work. And for that purpose, I'll refer to these studies as small. At the top, where we plotted the large studies, there are roughly an equal number of studies on either side of the mean. Toward the bottom, where we plotted smaller studies, there may be 5 or more studies to the right of the mean, but only 3 studies to the left of the mean. The concern is that there may have been studies that reported effects in this area, but that were not published and therefore not included in the analysis. The idea is that if we could somehow recover those studies and add them to the analysis, the mean effect size might shift to the left. To assess the potential impact of publication bias, I would proceed as follows. First, I need to decide if I expect studies to be missing to the left of the mean or to the right of the mean. The mean is here, and the null value is here. Non-significant studies will fall closer to the null value, which in this case is to the left of the mean. So that is where I would expect studies to be missing. I click View, Trim, and Fill. I click Look for Missing Studies to the left of the mean. There's an option to use either the fixed effect model or the random effects model to look for the missing studies. While we will be using the random effects model to conduct the actual analysis, there is still a convention to use the fixed effect model to look for missing studies. If I want to follow that convention, I make that selection here. And then I click Funnel Plot. Finally, I click Plot Observed and Computed. The trim and fill procedure determines that there is an imbalance with more studies on the right than on the left. On the assumption that the studies on the left actually do exist, but were never published, the method imputes those studies and adds them to the analysis. We can see them here. On the bottom, we now have two diamonds. Based on the original studies, the mean effect size and its confidence interval would be here. Based on the original studies plus the imputed studies, the mean effect size and its confidence interval would be here. To see the actual values corresponding to these diamonds, I can again click View, Trim, and Fill. As I mentioned before, there's a convention to use the fixed effect model for determining how many studies might be missing. Even if we adopt that convention, when we rerun the analysis with the inclusion of these studies, we still want to apply the random effects model. This section shows the results for the random effects model, and it's the one that we want to use. This row shows the results based on the 17 actual studies and corresponds to the open diamond. And this row shows the results based on the 17 actual studies plus the 2 imputed studies and corresponds to the closed diamond. It's important to interpret these numbers correctly. The main take-home message is this. If there is bias due to missing studies, the basic conclusions remain unchanged. We estimated the mean effect size as 0.51. If the true effect size actually is 0.44, the clinical utility of the drug is essentially unchanged. The difference between 0.51 and 0.44 is trivial in this context. Notice that I said if there is bias due to missing studies, because that might not be the case. The trim and fill procedure, like most procedures to assess publication bias, looks to see if the effect size for small studies tends to be larger than the effect size for large studies. If we find few studies here and more studies here, we might assume that these studies actually exist but are missing from the analysis. However, that might not be the case. It's entirely possible that small studies do actually tend to show larger effects. And in that case, the original value of 0.51 would be the value that we want to use. The bottom line is that the adjusted value of 0.44 is not intended to serve as the correct value. Rather, it's intended to serve as a kind of sensitivity analysis. It tells us that if there are studies missing, the basic conclusions would remain the same. CMA is able to run various other tests for publication bias. I won't discuss them here, but simply mention that these include the failsafe N, the rank correlation test, and Egger's regression test. Additionally, if you click View Report, the program will generate a detailed report that discusses all of these analyses and how to understand them. In part 1, I started by showing how we could estimate the mean effect size and the dispersion in effects. Then I took a tangent to discuss sensitivity analysis. We discovered that the basic analysis is robust. It is not dominated by any one or two studies. The results are relatively stable, and the key conclusions are not an artifact of publication bias. On that basis, let's return to the main results. The mean effect size is 0.51, which we elected to call moderate based on the clinical description. But we also know that the effect size in any given study may fall some distance from the mean. In part 1, I showed how we could use this data to estimate the distribution of true effects. And that distribution looked like this. At one extreme, there were studies where the drug had virtually no impact, and at the other extreme, there were studies where the drug had an enormous impact. To understand why this matters, let's consider another analysis. Suppose we had a drug with a mean effect size of around 0.50 and a prediction interval of 0.40 to 0.60. In that case, the drug would have pretty much the same effect size in any population. If someone asked, what will the impact be for this patient? We could say that for patients of this type, the predicted effect falls close to 0.50. By contrast, consider the actual results in the current analysis. The mean effect size is around 0.50, but the prediction interval is roughly 0.05 to 0.95. If someone asked what will the impact be for this patient, the prediction interval is so wide that it's not really useful. What we want to do is to identify factors that might explain some of this variation. Eventually, we would like to be able to say that for this patient, we expect the effect size to be near 0.1, and so the drug would not be recommended, while for this patient, we expect the effect size to be near 0.90, and so the drug would have a major effect. There are two procedures we employ to identify factors that are associated with the size of the effect. These are subgroup analysis and meta-regression. Here, I'll show how these procedures can be applied in this case. Let's return to the data entry screen. The columns over here hold data for variables that might be related to the effect size. This one is SUD, which stands for Substance Abuse Disorder, and each study is coded either Y or N. Y means that some of the study's patients were abusing drugs, and N means that the study excluded patients who were abusing drugs. We need to tell the program that this is a moderator variable. I double-click on the title, SUD. The column function is a moderator, and we also need to specify the data type. The options here are categorical, integer, or decimal. We would use integer if this was something like the year of publication, and we would use decimal if this was something like dose. In this case, we're dealing with categories, yes and no, and so we use categorical. Next, I want to assign a function to the column labeled dose. I double-click on the title, dose. The column function is a moderator, and the data type is decimal. Now we can return to the analysis screen. I click Run Analysis. I click Random Effects. I click Computational Options and Group By. The only option displayed here is SUD, and that's because this was the only moderator that was defined as categorical. I select SUD. I add a check mark to each of these options, and I click OK. Finally, I'll right-click on the column with the standardized mean difference, and sort from low to high. These are the studies that excluded SUD patients. The mean effect size is 0.58. And these are the studies that included SUD patients. The mean effect size is 0.16. To get a better sense of the difference between the two, I can hide the individual studies and display only the summary rows. To hide the individual studies, I deselect this button. For studies that excluded SUD patients, the mean effect size is 0.58. For studies that included SUD patients, the mean effect size is 0.16. I think it's clear that the difference is clinically important, and additionally, I can see that there is almost no overlap between the two confidence intervals, and so I expect that the difference in means will be statistically significant. We'll look at that in a moment. I'll click this button again to redisplay the individual studies. Next, I want to ask if this difference is statistically significant. I click Next Table. This section is labeled Mixed Effects Analysis. This is the section that I want to use. I'll explain later what it means. The mean effect sizes are the same ones that we saw a moment ago. For the 13 studies that excluded SUD patients, the mean effect size is 0.578. For the 4 studies that included SUD patients, the mean effect size is 0.161. To compare this mean versus this one, I can use a Q-test. The Q value is 6.117 with 1 degree of freedom and a p-value of 0.013. I would reject the null hypothesis that the mean effect size is the same here and here. I would conclude that the effect size is higher here. So, to recap, we've concluded that the difference between this mean and this one is statistically significant. I wanted to start with that conclusion. But in running these computations, I made a series of decisions. I need to discuss what those decisions were and why I made them. We also need to discuss what conclusions we can draw from this analysis, and equally important, what conclusions we cannot draw from the analysis. The first issue I want to discuss is the choice of a statistical model. As always, at the bottom of the screen, we can select either the fixed effect model or the random effects model. I selected the random effects model. Let's be clear about what that means. When we're performing a simple analysis without subgroups, the difference between fixed effect and random effects is as follows. We would use the fixed effect model if we believed that all studies were based on the same population and were identical to each other in all important respects. For example, the fixed effect model would apply if the true effect size for all studies fell directly on this line, and the observed effects deviate from the line only because of sampling error. The true effect size is the same in all studies because all studies are based on the same population. The results would apply to that population only and could not be generalized to any other populations. By contrast, we would use the random effects model if we believed that studies were based on different populations or varied from each other in meaningful ways. For example, the true effect size for the various studies might fall along this line. The true effect size varies from study to study because each study is based on a unique population. The results would apply to the universe of comparable populations. As I've explained elsewhere, on that basis, the random effects model is almost always the one that we want to use. The same idea applies here, except that now we apply this criteria within subgroups. And again, on that basis, the random effects model is almost always the one that we want to use. For example, consider the studies in this subgroup. If we believed that these studies were all based on the same population and were identical to each other in all important respects, we would use the fixed effect model to estimate the common effect size here, and that effect size would apply only to that one population. However, that is clearly not the case. While these studies are similar to each other, in the sense that they all excluded SUD patients, they are not based on the same population, and they do vary from each other in many important ways. Therefore, we apply the random effects model here. And this allows us to generalize the results to the universe of comparable studies. Similarly, if we believed that all of these studies were based on the same population and were identical to each other in all important respects, we would use the fixed effect model to estimate the common effect size here, and that effect size would apply only to that one population. However, again, that is clearly not the case. While these studies are similar to each other in the sense that they all enrolled SUD patients, they are not based on the same population, and they do vary from each other in many important ways. Therefore, again, we apply the random effects model. And this also allows us to generalize the results to the universe of comparable studies. Whenever we use the random effects model, we need to compute tau squared, the variation in true effect size across studies. In a simple analysis, when we have only one set of studies, we compute tau squared across all those studies. But when we have subgroups, we must compute tau squared within subgroups. For the first set of studies, tau squared is estimated as 0.014, and for the second set of studies, tau squared is estimated as 0.071. At this point, we have two options for how to use these estimates. We can pool the two estimates. If we do that, we will get a pooled estimate of 0.021, and then we can use that pooled estimate for both subgroups. Or we can apply each estimate to the corresponding subgroup. Since tau squared plays a role in the weights assigned to each study, the decision that we make will affect the values that we see here and here. The first option is to pool the two values to get one common estimate, and then apply that estimate to both subgroups. And that yields the numbers that I see here. This mean is 0.578 with this confidence interval, and this mean is 0.161 with this confidence interval. The second option is not to pool the two estimates of tau squared. Rather, we would use the value of 0.014 to compute the statistics for this set of studies, and we would use the value of 0.071 to compute the statistics for this set of studies. That would yield the numbers that I see here. This mean is 0.572 with this confidence interval, and this mean is 0.175 with this confidence interval. In almost all cases, I want to pool the estimates. Why do I choose to pool the estimates? The reason is that an estimate of tau squared based on a small number of studies is not reliable. The estimate here is based on 13 studies and is not very reliable. The estimate here is based on 4 studies and is not reliable at all. So, if we used the two estimates without pooling, these estimates would be poor. By contrast, if we pool them, we have an estimate based on 17 studies, which is better. Obviously, when we pool the two values, we're losing information. If the variance in effects for this kind of studies is actually greater than the variance in effects for this type of studies, we lose that information when we pool. However, the amount of error that we introduce by pooling is likely to be much less than the amount of error we introduce by estimating tau squared based on 4 studies. And so this is the option I've chosen here. How do I specify which option I want to use? I click Computational Options, Mixed and Random Effects Options. In the top part of this panel, I choose the option to pool the two values. If you'd like to see the value of tau squared, click Next Table. The value of tau squared is displayed here. If I've selected the option to use separate estimates of tau squared, then tau squared for the first subgroup is 0.014, and tau squared for the second subgroup is 0.071. And these are the statistics that we would get for each group. If I've selected the option to pool the estimates, then tau squared for each subgroup is 0.021, and these are the statistics that we would get for each group. This is the option that I would use in this analysis. To this point, I've explained that we want to choose a random effects analysis. Now I need to discuss why this is called a mixed effects analysis rather than a random effects analysis. The reason is that we need to choose a statistical model at two levels. Within subgroups, we're using random effects. That is, we use a random effects model to synthesize the data from these studies and yield these numbers, and we use a random effects analysis to synthesize the data from these studies and yield these numbers. At the same time, however, we're using a fixed effects model to select the two subgroups. And those are the subgroups which exclude SUD patients or include SUD patients. The two subgroups are fixed. The word fixed here does not mean that the two groups are the same, since obviously they're not. Rather, they are fixed in the sense that they have been selected or identified. In other words, we care about these specific subgroups only. We want to know the mean effect here and here. We will not be generalizing from these two subgroups to other subgroups. To specify that we will be using fixed effects for the subgroups, I click Computational Options, Mixed and Random Effects Analysis, and this selection is made on the bottom part of the panel. And I select the option to combine subgroups using a fixed effects model. To recap, we'll be using the fixed effects model to identify the specific subgroups that we care about. We set that here. And we will be using the random effects model within subgroups, and we set that here. Since we're using fixed effects at one level and random effects at the other, this is called a mixed effects model. I discussed this further in my workshop, but these are almost always the options that you will want to use. Now let's return to the key finding. The difference between this mean and this one is statistically significant. What does that tell us? The answer is probably not what you'd expect. I am able to say that the effect size here was greater than the effect size here. However, I cannot say that this is due to the fact that these studies excluded SUD patients while these studies enrolled SUD patients. Let me say that again. I can say that the effect size is higher here than here, and that the difference is statistically significant. But I cannot say that this difference is due to the inclusion or exclusion of SUD patients. And that holds true despite the fact that all the studies in the analysis were randomized controlled trials. This may seem counterintuitive, so let me unpack this. Consider the Adler study. The effect size is 0.531 with a confidence interval of 0.253 to 0.809. We can test the null hypothesis that the mean effect for the treatment was no different than the mean effect for the placebo. The z-value for that test is 3.742, and the p-value is less than 0.001. Can we conclude that the treated group did better than the placebo group? The answer is yes. Can we conclude that the drug was responsible for this difference? Again, the answer is yes. We can draw this conclusion because this study was a randomized controlled trial. Adler started with a sample of patients. Some were randomized to the drug, while others were randomized to a placebo. Assuming that the randomization process worked properly, the two groups are similar to each other in all important ways except for this one, whether they received the drug or the placebo. Therefore, if one group does better than the other, we can assume that this is due to the impact of the drug. This logic applies to every one of these studies, and it also applies to the mean effect size for this subgroup of studies. In each study, the use of randomization allows us to assume a causal relationship, and that protection carries over from the individual studies to the summary effect. If the mean effect size is statistically significant, we can assume that the drug is responsible. And so, for this subgroup of studies, we conclude that methylphenidate is more effective than placebo for increasing cognitive function. The same idea applies to the studies in this set. The mean effect size here is not statistically significant, but if it was, we could assume that the drug was responsible. By contrast, consider what happens when we want to compare the mean effect size for these studies versus the mean effect size for these studies. As we saw a moment ago, the difference in means is statistically significant. And so we can say that the drug is more effective in these studies than it is in these studies. But we cannot say that the inclusion or exclusion of SUD patients is responsible for the difference. And the reason is that we did not use a random process to assign studies to include or exclude SUD patients. Therefore, there might be other variables which are confounded with SUD. For example, suppose that the studies which excluded SUD patients tended to use a higher dose of the drug, while studies which included SUD patients tended to use a lower dose of the drug. We chose to call these groups SUD excluded versus SUD included, but it's possible that we could also have labeled these studies high dose and low dose. And it's possible that dose, rather than SUD, is responsible for the difference in means. Or it's possible that studies which excluded SUD patients tended to be long-term studies, while studies that enrolled SUD patients tended to be short-term studies. And it's possible that study duration, rather than SUD, is responsible for the smaller effect that we see here. Again, we chose to call these groups SUD excluded versus SUD included, but it's possible that a more appropriate label would have been long-term studies versus short-term studies. In other words, it's possible that study duration, rather than SUD, is responsible for the difference in means, and so on for any other potential confounds. The key point is that even when all the studies in the analysis are randomized controlled trials, the difference between subgroups is almost always observational rather than causal. So we can say that the effect size was larger in studies that excluded SUD patients, but we cannot say that this is due to the exclusion of those patients. It might be due to that, but it could also be due to some other factor which is confounded with SUD. There's one more point I wanted to make before moving on. This is the mean effect size for studies that excluded SUD patients, and this is the mean effect size for studies that enrolled SUD patients. This is the mean effect size across all studies. We need to ask if it makes sense to report this value. In some cases, it will make sense to report this value, and in some cases, it will not. But it's important to understand what this value represents. The mean here is a weighted mean of this mean and this one. Since this subgroup has more studies than this one, it will tend to carry more weight in computing the overall mean. The mean effect size here can be thought of as the mean effect size in a universe where roughly 75% of the studies exclude SUD patients and roughly 25% include SUD patients. I'm not sure this is a universe that I would care about, and so I would choose to remove the line with the overall effect size. And to do that, I deselect this button, and the overall effect size is now hidden. On the other hand, if the mean in all subgroups had been comparable, I may have elected to display the overall mean. So that's a basic look at subgroups analysis. Now let's move on to a meta-regression. We just looked at SUD as a potential moderator. The other potential moderator we want to look at is dose. Since dose is a continuous variable, we cannot use subgroup analysis to look at its relationship with effect size. Instead, we'll use meta-regression. First, I need to remove the subgrouping. I click Computational Options, Group By, and Reset. Then, I click Analysis, Meta-Regression 2. This frame shows all the moderators I had identified on the data entry screen. These are dose and SUD. Note that this includes both continuous and categorical moderators, since both can be used in a meta-regression. I click on Dose. I click Add to Main Screen. The program moves dose from here to here. I close this panel. I add a check mark for dose, and then I click Run Regression. This table reports the statistics. I'll come back to this momentarily, but first I'd like to see a plot of the data, which will provide some context for understanding the statistics. I click Scatter Plot, and the program switches to this screen. The title is Regression of Standardized Difference in Means on Dose. The x-axis is dose. The scale goes from 10 to 100. The actual doses range from roughly 30 milligrams to 80 milligrams. The y-axis is the effect size. The scale goes from minus 0.80 to plus 1.60. The actual effects range from minus 0.25 to plus 1.30. The regression line moves from the lower left to the upper right. As the dose gets higher, the effect size gets higher. For studies where the dose is 30 milligrams, the predicted effect size is roughly 0.25. For studies where the dose is 80 milligrams, the predicted effect size is roughly 0.75. So, as the dose increases by 50 milligrams, the effect size increases by roughly 50 points. The fact that the number of units matches the number of points is simply a coincidence. To see the actual numbers, let's return to the main results screen. This table shows the relationship between each variable and effect size when all other variables are held constant. In this case, the only variable in the equation is dose, so this is simply the relationship between dose and effect size. As dose increases by 1 milligram, the effect size increases by 0.0094. I could round that to 0.01. As dose increases by 1 milligram, the effect size increases by roughly 0.01. Or, as dose increases by 10 milligrams, the effect size increases by roughly 0.10. And as dose increases by 50 milligrams, the effect size increases by roughly 0.50, which is what we saw in the plot. As dose increased from 30 to 80, which is an increase of 50 milligrams, the effect size increased by roughly 0.50. We can also test the null hypothesis that there's no relationship between dose and effect size. In other words, that the true coefficient is 0. The z-value for that test is 2.14, and the p-value is 0.0321. If we're using a criterion alpha of 0.05, we would reject the null hypothesis that there is no relationship between dose and effect size. Next, we move to this table, where the table at the top provides information for each covariate, with all other covariates held constant. This table provides information for the full set of covariates. Put another way, this asks if all the covariates as a set are able to explain any of the variance in effect size. In this case, since there's only one covariate in the analysis, this analysis is the same as this one. This analysis uses a Q-value rather than a Z-value. The Q-value is 4.59 with 1 degree of freedom and a p-value of 0.0321. Since there's only one covariate, this p-value is addressing the same null hypothesis as this one, and the two values are therefore the same. Notice that this block actually has two parts. The part we just looked at addresses the question, do the covariates explain any of the variation in effects? The second part asks if the covariates explain all of the variation in effects. To explain what the second part means, let's have another look at the plot. We have the regression line, and we have the individual studies. The null hypothesis being tested in the second part is that dose is able to explain all of the variation in effects. Put another way, the null hypothesis being tested is that the true effect size for all studies falls directly on the regression line. Of course, most of the observed effects fall some distance from the regression line, but the null hypothesis refers to the true effects rather than the observed effects. The null hypothesis is that the true effect size for this study is actually here, and the observed effect size is here only because of sampling error. Similarly, the true effect size for this study is actually here, and the observed effect size is here only because of sampling error, and so on for all the other studies. To test this null hypothesis, we use a Q-value. The Q-value is 24.12 with 15 degrees of freedom and a p-value of 0.0631. By convention, we use a criterion alpha of 0.10 to test this null hypothesis. Since 0.06 is less than 0.10, we would reject this null hypothesis, and we would conclude that dose does not explain all of the variation in effects. Taking these two elements together, we conclude that dose explains some of the variation in effect size, but not all of the variation in effect size. Similarly, there is a statistic here called the R-square analog, which is 29%. This tells us that the covariate is able to explain some 29% of the variation in true effects. This statistic is called the R-square analog because it is analogous to the R-squared statistic that we use in multiple regression in primary studies, but does differ from that statistic in some important ways. To this point, I've been using the z distribution to compute the confidence intervals and p-values for the coefficient and for the overall omnibus effect. However, it's generally a better idea to use the Napartung-Siddiq-Yankman adjustment. This adjustment yields a confidence interval and p-value that tends to be more accurate than the one we get using the z distribution. I can click Computational Options Nap-Hartung. Now, this table shows us the adjusted confidence interval, a t-value rather than a z-value, and an updated p-value. Similarly, this table shows us the f statistic rather than the q-value and an updated p-value. This was intended as an overview of the meta-regression module. In my workshops, I go into a lot of additional detail. For a more complete discussion of meta-analysis, consider subscribing to our workshops, which are now available online as well as in person. For information, visit metaanalysisworkshops.com. This is also where you can download the free paper about heterogeneity. In this analysis, I used the software Comprehensive Meta-Analysis. For information about the software, please visit metaanalysis.com. My name is Michael Borenstein. My email is michael@metaanalysis.com. Feel free to contact me with any questions or comments.